Hey everyone, and welcome to This Explainer. I'm your host, and as a materials scientist who spent, over 15 years now deep in the weeds of electrochemical energy storage, I am just incredibly excited to take you on this journey today. We're going to uncover exactly why redox flow batteries, or RFBs, are really the ultimate solution for grid-scale energy storage. If you've ever sat back and wondered how we actually practically transition our entire planet to run on clean energy, well, you are definitely in the right place. We're going to dive into the chemistry, the engineering, and honestly, the sheer visionary brilliance behind what I like to call the vanadium revolution.
Okay, let's just jump right in with the question that literally keeps energy grid operators awake at night. Why can't the grid just rely solely on wind and solar? I mean, it sounds simple enough, right? Just build a ton more solar panels and wind turbines. But here's the catch. The electric grid is a real-time machine. Supply absolutely must perfectly match demand every single second of every single day. If the wind suddenly stops blowing or a big cloud blocks the sun, power generation drops instantly. Without a massive, totally reliable way to store that energy when it's abundant and discharge it the second it's needed, relying entirely on intermittent renewables would literally cause the grid to collapse.
So this brings us to what we call the energy storage gap. Basically, it's the missing link between intermittent renewables and a stable electric grid. Right now, without large-scale, long-duration energy storage, the whole renewable revolution is, well, it's effectively stalled. We're facing this incredibly high-stakes engineering challenge. Think about it. We have the technology to generate clean power, but we are completely bottlenecked by our inability to bank it efficiently at a massive societal scale.
So the absolutely crucial point here is this. If we really want to achieve a 100% renewable grid, we need a technology that goes far, far beyond the limitations of conventional solid-state batteries. You all know lithium-ion, right? It's in your phone, your laptop, probably your car, and it is fantastic for those applications. But for the grid, it degrades over time, it carries pretty serious fire risks at massive scales. Actually, scratch that. The biggest issue is that its power and its energy are permanently locked together in one physical package. To get to 100%, we literally have to rethink the battery from the ground up.
So let's get into Section 1, the mechanics, decoupling power and energy.
Let's peel back the curtain a bit and visualize the inner workings here. I actually love using a cardiovascular analogy to explain this because it's just so elegantly biological in its design. A flow battery has three main components. First, you have the tanks. These are like the lungs of the system, storing the energy in massive vats of liquid. Second, the pumps. This is your mechanical heart, actively circulating that liquid. And third, the cell stack. This acts like the capillary bed. It's the exact site where the critical electron exchange actually happens. Let's look at the formal definition for a second. A redox flow battery, or RFB, is an electrochemical energy storage device where energy is stored in liquid electrolytes that are then pumped through a central power-generating stack. By separating the power generation, which again happens in the stack, from the energy storage, which happens in the tanks, we completely break the physical limitations that hold conventional batteries back. Notice how this fundamental architecture brilliantly decouples the storage and the cell into two totally distinct entities. In a traditional battery, if you want it to last twice as long, you have to buy a battery that is twice as powerful and twice as expensive. It's a package deal. But in an RFB, it's totally different. If you want more power, say to handle a sudden spike in air conditioning use during a heat wave, you just add more cells to the stack. But if you want more energy, like to keep the lights on through a long windless night, you simply build larger tanks and add more liquid. It's scalable in a way that solid-state batteries simply are not.
All right, moving on to Section 2. The vanadium miracle. One element, four valences.
So, vanadium. This is the undisputed star element of our explainer today, and it is the absolute protagonist in our fight against battery degradation. It's incredibly unique because it can exist in four distinct stable oxidation states, or valences, in an aqueous solution. On the negative side of the battery, it cycles back and forth between V2+ and V3+. On the positive side, it cycles between V4+ and V5+. Now, why does this matter? Because it allows us to use the exact same element on both sides of the battery.
I really want you to try and picture this visually on a microscopic level. Imagine those vanadium ions flowing into the cell stack from their massive tanks. As the battery charges, on the positive side, the fluid shifts, stripping electrons and pushing the ions from V4+ up to V5+. Meanwhile, those exact same electrons travel through the external circuit over to the negative side, reducing the vanadium there from V3+ down to V2+. All the while, hydrogen protons are sliding across this specialized proton exchange membrane right in the middle to keep the whole system electrically balanced.
It's just this beautiful, continuous, flowing dance of electrons. But here is where the real magic happens. In other flow batteries that try to use two different metals, the membrane eventually leaks. The metals cross over, contaminate each other, and boom, the battery is ruined. It's a fatal flaw. But because a vanadium redox flow battery uses vanadium in both tanks, any microscopic leakage across the membrane just mixes vanadium with, well, vanadium. It doesn't ruin the electrolyte at all. This simple fact gives the battery a practically infinite theoretical cycle life. If the tanks ever get slightly out of balance, you just chemically rebalance them, and you are right back to 100% capacity.
Which perfectly sets up Section 3, Engineering Marvels, Scalability, Safety, and Recovery.
Let's pivot to the practical engineering advantages for a minute. Draw a stark contrast in your mind right now. Conventional lithium-ion locks power and energy together in a solid, rigid structure. Every single time it charges and discharges, that solid structure physically expands and contracts, which causes microcracking and permanent degradation over time. Vanadium RFBs, however, keep power and energy fully independent in fluids. The electrodes in the stack, they're just inert carbon felt. They don't even participate in the chemical reaction. They just provide a surface for it to happen on. The liquids themselves are infinitely renewable.
And then, of course, we have to talk about the safety profile. Listen, if you're going to put megawatts of energy storage right next to a heavily populated city, it absolutely cannot catch fire, period. Vanadium RFBs offer ultimate grid safety. The electrolytes are non-flammable because they are aqueous, meaning they are mostly just water dissolved in a sulfuric acid solution. They operate incredibly comfortably at room temperature, right between 10 and 40 degrees Celsius. Because of this, there is literally zero physical risk of thermal runaway. Massive liquid tanks of aqueous electrolytes are essentially fireproof, which is a game-changing advantage over highly volatile solid-state grid batteries.
Take a look at this data on capacity restoration over 50 cycles. Now, over time, flow batteries can experience a very slight capacity fade, just due to an unequal transfer of water and ions across the membrane. But look closely at the red line compared to the black line here. This data is amazing because it proves that even when capacity fades, we can completely restore the energy efficiency without replacing the expensive electrolyte and without ever having to disassemble the battery stack itself.
So, how exactly do we pull that off? Through some cutting-edge chemical recovery. By simply mixing the positive and negative electrolytes together and adding a highly precise amount of a reducing agent, something like oxalic acid dihydrate, we can completely rebalance the valences. This incredible research means that the cycle life of a vanadium RFB can essentially be extended indefinitely. You don't throw the battery away after 10 years like you do with other tech, you just give the liquid a quick chemical tune-up. All right, let's wrap this up with Section 4, Powering a Renewable Future.
Let's zoom out to the macro level now. We've looked at the microscopic ion exchange, we've looked at the engineering of the tanks, but what is the real global impact of scaling this technology? I want to read this quote directly from the research literature because it just completely hits the nail on the head. The decoupling of storage and power generation enables a flexibility of design and easier energy capture, allowing for large-scale MW range storage systems. Megawatt range. Guys, that is the scale of small cities. This isn't just a battery. This is industrial-scale energy infrastructure. These massive liquid batteries are the cornerstone that will allow us to capture boundless solar heat and wind power and finally dispatch it with the exact same reliability as a traditional fossil fuel power plant.
So I'm going to leave you with this final thought to chew on. We've seen the chemistry, we've seen the infinite cycle life, and we've seen the completely unmatched safety profile. Are these giant liquid flow batteries the final key to unlocking a 100% renewable planet? Speaking as a material scientist, when I look at the vanadium revolution, I see a future where clean energy is never wasted and the grid simply never fails. Thank you so much for joining me on this explainer. Keep questioning, keep learning, and